voltage stability, impact and solution. So what is the impact that we discussed? Voltage collapse can happen in the system, low voltage scenario impacting the load. If you operate the loads at low voltages, it is deteriorating the loads, means the loads will having a heating issue and its life will also reduce. It will also impact your local equipment at your household level, and there can be a result into the different kind of instability. What is the solution? Simple solution is that if you want to avoid voltage collapse, you provide adequate reactive power into the system. That's the simple explanation of all the means. Whatever the problem is there, there is a single solution: provide adequate reactive power resources into the system at different nodes. Nothing more is required. But that planning itself is a slightly complicated process in itself, because reactive power is a local control. So at each local level, you have to access how much reactive power will be required. Not only one point of the time, throughout the entire year, throughout the next 10 years, 5 to 10 years, how your load behavior will be like this, how much the loading on the transmission system will be like this. So all these aspects has to be taken care while designing the reactive power resources at any point of time on any substation. So these are some of the, means solution that is there. One is that you provide adequate reactors or capacitor. So these are a static devices, means 120 MVAR reactor. If you start switch on, then 120 MVAR will come into the system directly. 80 MVAR, if you switch on, 80 MVAR will come into. So these are static devices that is there placed in the system. Then what you can do is that you can do another way of doing control is transformer tap change. So what is basically a transformer? Transformer is like this. It is the one per unit, right? There are two different voltage level. This is 400. This is 220. Both are operating at per unit, one per unit. Okay. Let us say the actually in generally the voltage of 420, this was operating this due to some loading scenario. The voltage on my for this side has went up to 420 kV, while this 210 voltage is basically it is operating at, let us say, 222 or 223, because we have a good loading support at the loading level, means at the distribution level. While at the transmission level, what I'm observing is that due to the lightly loaded scenario of other transmission line, the voltage is on the higher side, on the 400 kV side. So if you see in terms of per unit, it is nearly to 1 per unit, while it here it is very high, it is 1.05, right? So how the reactive power will start flowing into the system? This reactive power will start flowing into the 400 to 220 kV system, right? Because the voltages will be higher on the 400 kV side and lower on the 220 kV side. So you are trying, the voltage of 400 is injecting reactive power into the 220. But optimal planning is light operation is also like that. You don't need to transfer any amount of reactive power from high voltage to low voltage or low voltage to high voltage. It should not be there. Both system are physically, means physically it has been, not physically, electrically is, right? So in that terms, means we don't want that reactive power flow should happen and one part of the system, high voltage system, should impact low voltage system that much. So what you will try to do, you will try to increase the voltage on this side so that you can minimize the reactive power flow from this side to that side of the system. So if you do that, your reactive power support will come into the, by doing the tap changing, you can manage the voltage into the system. Then you have dynamic reactive devices which have the capability like a generator itself. They can dynamically control the active and reactive power, because these are basically what you can say that power electronics based devices. So power electronics based devices, they have a very faster control, right? So SVC and STATCOM has a very fast control, due to which they can absorb and inject reactive power very quickly into the system. During any fault, you can inject the reactive power, and as soon as the fault is clear, you can come back to the original position. And whenever there is a sudden, there is a loss of the generator, then reactive power will suddenly increase into the system. It can directly, again at that point of time, it will again inject into reactive power into the system to control the voltages. So these are the means different kind of reactive power equipment that is available, or the techniques that are available. These are equipment, this is equipment, this is the transformer tap changing. That is one resource that we are having to optimize the means voltages in, or the optimize the reactive power flow into the system. In case we are not able to control from these kind of things, then there is a under voltage load shedding. So wherever any utility faces significant voltage situation or anything they have planned, but it is not in the transmission line has all still not in place, but they have to supply that much of power into the that particular voltage level, then what they will do is that for managing the system during any contingencies when the voltages will be very low, which can result in voltage collapse, what they will do is that they will provide under voltage load shedding. So what can it do? It can operate at 0.8 or 0.9 per unit under voltage. As soon as it detects under voltage, it will loads to reduce the loading on the transmission lines or the distribution line, so that the voltages on the transmission and distribution system can be improved. But in generally, we should try to avoid by adequate planning of the transmission and distribution system and associated reactive power support.
Sir, here we can add generator control also, generator side reactive control.
Yes, that is already there. This I am just telling you that why the generator is already doing that activity. Generator is
Yes.
already, you have informed him that okay, your part is that you control the reactive power support into the system this much, because this is in operational control. And the reactive power in generally, why I am always try to avoid the generator point of control is that you have to think in a manner that generator may be there and may not be there into the system, right? Right now what you are facing is that many a times your whatever the generator that you were utilizing to control the reactive power, many of them are not available due to the increase of RE generation. So that is also a problem that we are facing. So another thing is that for reactive power, you have to schedule the generator also. We do the scheduling for the active power, but we don't do any scheduling for the reactive power. So what happens is that you are also facing the same issue. When you go to a generator, you face high voltages, you ask them to absorb the reactive power, they will have a lot of means they will tell you a lot of stories on that regard, that these are the issues that I am facing. So those
Yes, sir.
kind of things are there. So until unless you provide them some flexibility, some kind of support in providing, or some kind of compensation in providing the reactive power support to the system as a form of ancillary services, the control is not that flexible in terms. While the control, you have a reactor capacitor in your control, transformer tap changing in your control, SVC STATCOM in your control, UVLS is in your control, right? But whether you are able to completely dictate everything, whatever you are telling the generator to do, are they doing that? Not completely possible. They have lot of issues, because generator will tell you that simple thing is that they have high voltages. If you ask them, okay, absorb more generating power, they will tell you the issue is that the LV side, yeah, GT means my GT type is like that. The LV side, the voltages will go so down that I am going to face a lot of problem with my other, means what kind of auxiliary system, auxiliary loads are there. So they will be facing a lot of challenges during any voltage fluctuation. So these kind of issues are there. So that's why in generally solution side, if you are not going to put a generator for reactive power control, right?
Yes, sir.
You
Yes, sir.
if I ask you that there is a transmission system is there is a problem of reactive power at this point, so what you will try to do? You are not going to put a planning side that okay, let us put a generator over here. It is not like that, na. You put reactive power resources there. So that's how this planning side is concerned. That is a additional flexibility that a operator is having as a part of, not as a part of direct planning. It is a flexibility that I am having, that okay, that these generators are there which can provide me reactive power support. But actually, if you ask me that how you are controlling, these are the basic mechanism. And problem is that relying on the means we generally rely on the generator to provide all the support of reactive power. Then this becomes a very big challenge for the system operation. You will see that if you too much rely on the generator and you do not plan, and many of the times we have seen that utilities have not planned the reactor and capacitor at that time, and they have faced a lot of repercussion, and for ultimately they have, but certainly in future they have planned again, but those dependency on the generator is not a viable solution if you
Right,
means
sir.
in
Right.
terms of the reactive power control.
Yes.
Sir, can you explain under voltage load shedding again, sir? Above fours are okay. How it
Okay,
will
okay,
be doing?
just I will tell you. Aja, do you know this? There are few kind of things that I will tell. You have seen frequency control also, right? You have learned about frequency, that there is a primary, secondary, tertiary. There is again a frequency control which is called emergency frequency control. You have a generating plant where you will see that there is a either over voltage frequency trip or low, means under, over frequency trip or under frequency kind of trip. It is for protecting the generator itself, right?
Speed,
Same side.
speed governor is there who will be taking care of all these things.
Yeah, yes. If you go with the, if you go with the hydro, you will find this high frequency trip setting is there, right? And if you go to the this one thermal, you will see that there is a low frequency trip setting on the governor side, is the turbine governor side, right? So that speed control, I mean, you have to maintain, because otherwise the eccentricity will lose, too much of vibration will be observed. So this kind of controls for safety of the equipment is there. Let us say if you don't put this kind of safety, then what will happen? These damages will be non-recoverable, right? Means you will not be able to restore the system very quickly after the disturbances if these trip settings are not there. It is safeguarding. So that's the frequency part. Voltage part, at your load, at your household load, you have a trip setting in your AC, under voltage load trip. You have trip setting in even in your different equipment, low voltage trip setting or over, means different kind of protections are placed in your devices, right? So under voltage devices, you have this kind of under voltage trip setting even in your this what you call ACDB also in your substation also, right? So these trip settings are in place at various location. This under voltage, basically under voltage detection, and you do the trip setting basically to, why you are doing it, to so that you do not damage the equipment basically. That's the purpose of it. How come the under voltage load shedding is, when let us say this is a transmission line, okay, and this is the load, okay. So what was planned is that this P amount of 100 megawatt was required to be transferred, okay. And the voltage is V1 is, let us say, 1 per unit, and it is also 1 per unit. And these two transmission lines are present, okay. Now let us say this demand is increasing and it is going to, and this 100 megawatt, this can be done with two transmission line in place. Even if one of the line trips, still the voltage will be within the limit. One, let us say it was 1. This is 1. If one transmission line trip, it is again going to 0.95 only, and 0.95, and with higher angular separation, this we can still transfer 100 megawatt. How we can do that? Let us say 1 into 1 into sine delta, let us say, and this is X, right? So this was the original transfer. Let us say what will happen is that 0.95, 0.95, and this is now 2x, right? Because this one, let us say, okay, this is 2x and this is 2x. Okay, so if you have this parallel operation, it is x, both line in service. single line in service, it will act as 2x. So what you will do is that here the sine delta will be very high, right? If you have to transfer same 100 megawatt amount of power. Let us say if I increase this 100 megawatt, it was a stable operation, 0.95 voltage are within limit, angle is also within limit. Even if n-1 is there, there is no issue in my transferring of that much of power into the system. Let us say I make it 200 megawatt. My projection is that the load is going to increase to 200 megawatt. So what should be a planner vision is that you need to know that, okay, this load can go up to 200 megawatt in next 5 years. So I need to provide another transmission line over here so that even if one of the line trips, still I am able to transmit 200 megawatt of power without crossing the operational voltage limits, right? So let us say this was the condition. However, there can be many situations. This transmission line has not come into the operation. It is still under construction or under discussion. And this load has come to this point, 200 megawatt. So what you can do, whether you will be supplying this load or not, you will be trying to supply this load. How you can do that? So one thing is that simple thing is that I'm not going to feed this 200 megawatt of load because it is crossing my limits. N-1 is not being it is not stable during the n-1 operation. If one line trips, then my entire system can collapse. So I will not be going to supply this additional 100 megawatt. Even if it comes, I will keep it out. But that's not the practical case. You have to supply that amount of load, right? So in those situations, what you will do is that as soon as you put under voltage relay over all these loads, loads will not be one. It will like one substation here, one substation here, one substation that is being fed from this main substation, right? This one. So what you will do is that, let us say I have to, in case of any tripping, I have to bring this 200 megawatt immediately to 100 megawatt so that my voltage are within 0.95. So what I will do is that I will check what will be the voltage drop that I am going to absorb with n-1. Let us say if it is 1 per unit, if it is going to 0.8. Okay. So my intention is that simple as that. If my voltage, I will put some voltage sensing relay at all these loads, whatever loads I wanted to cut so that I can, this is total 200 megawatt. I will put UVLS relays on 100 megawatt of the loads. And as soon as it senses 0. Below the voltage is going less than 0.95 or 0.9, whatever the voltage I select, if it is goes below this value for, let us say, 3 seconds, 1 second, 2 seconds, depending upon my stability criteria, whatever I have observed that at what point the voltage collapse will happen. So if I have that much of margin, so this time delay will depend certainly on the stability at how much time I have having available with myself so that the system will be stable in that particular portion unless there is a other contingency. So if I know this voltage drop and I have this time limit window, then I can design a UBLS setting that, okay, if the voltage is this and time is this, if it is persisting for this much of duration, trip all these loads because it is indicating that the one of the transmission line which was operating is going out of the system. So you have to curtail the loads so that that voltage can be maintained within the operational limit. So this is kind of emergency kind of thing. UBLS is like you generally do not plan. You plan only when you are actual planning has not come into the place for maintaining the stability. So this is what the UBLS means, under voltage load shedding relays. So you can see that this is the example. Load, if load keep on increasing, bus voltage is decreasing and it has reached this point, then suddenly trip this much amount of load. So the voltage has come back to the operational limit. So this is the UBLS kind of thing. Fax devices, you can see that suddenly there is a voltage drop due to the fault. Suddenly the fax devices has injected that much of reactive power. And as soon as the voltage goes out, it means this drop goes out, sudden drop due to any fault, it goes out due to the operation of the protection system. Then it's immediately it has withdrawn its reactive power support. So this is the fax devices. While capacitor on and reactor on off, you do all these operations based on the bus voltage, where the bus voltage is going on the this limit, lower limit, then you immediately switch on the capacitor. Again, due to the load changeover, it is going to upper limit. Then you switch off the capacitor. Again, it has come down and still it is going up. Then you switch on the reactor and then it is going down again down due to the loading limit of the system or the change in the load in the system. Then again, you do this kind of switching of the reactor on and off. So this all this goes on simultaneously during the operational phase when the real-time operation is being done. Just one example, how the voltage collapse. We can see that this is a generator, this is a bulb is there, okay? So if we keep on continuing adding more bulbs, so then you can see that the voltage is reducing and the power is slightly reducing. Okay, so your voltage is you are going, certainly the voltage keep on dripping, keep on dropping, keep on dropping. If you are not providing any reactive power support into the system. Okay. So you are coming from the controllable zone to uncontrollable zone, and this is the where the voltage collapse will happen. So everything, whatever that this generator is not able to provide the reactive power support after a certain point of time when its load angle limit has reached or when the field excitation limiters has already reached its limit. So we will face a voltage collapse. So how you can do this voltage collapse containment, increase generation, reduce demand, increase reactive power support, reduce power flow on heavily loaded line by routing this by utilizing parallel line or you utilize fax devices, block OLTC action at transmission level, reduce transformer tap at distribution level, brownout situation to avoid the blackout. So this kind of action that is being taken. So basically, I was telling you the compensation. You need to provide a good compensation. Like here, you are providing the same situation. You are providing capacitor bank at each of these locations. So you don't face the voltage collapse situation. Coming back to this, I told you about this is the how the voltage is being controlled in the system, right? The next point is that from where you are getting the strength, that operator is getting the strength for this kind of thing. Which part the planners is have to do this planning, reactive power compensation planning, from where it is written. This is also a very good thing that we should know. Means these are the where these regulations are there. So IGC, Indian Electricity Grid Code, states that reactive power compensation and other facilities shall be provided by STUs. First thing, STU as well as the users connected to ISTS as far as possible in the low voltage system close to load point. Why load point? You have to put the load at unity power factor. To maintain the load at unity power factor, you will be helping the system without, because it will avoid the need for exchange of reactive power to from ISTS to maintain the ISTS voltage within the specified range. Why? Again, that same transformer concept, 400, 220. If you maintain it at 220 itself, then, and this is already being planned at 400 kV. No, STU in generally plan their system below 220 and below sub transmission and distribution level, right? ISTS system, they have also ISTS system 400 and above also. Some STUs have 765 kV also. But in generally it is 220 majorly distribution connecting all their generators, all their major loads, and it is at 220 kV levels. And it is getting connected at ISTS either through their own 400 kV substation or through the 220 kV lines connecting to the ISTS system, right? So the STU purview is on the distribution, meeting the loads, while the ISTS purview is that all major large power plant, they are getting connected and the transmission system to build to transfer the power from this place to that place. So one side this is being planned, another side this is being planned. So STU is planning this, CTU is planning this. There should be a very balance in when you plan this, there is an active power balancing is generally considered. But at the same time, you need to do the reactive power balancing or do the reactive power planning in that way that this whatever the CTU will plan, it will be able to maintain the voltage of this 400 kV or above 765 kV level ISTS system to 1 per unit. It will not provide any reactive power support or exchange any reactive power to the 220 kV system. Same thing should also happen from this side. So the thing is that again the thing is that this person already connected to the grid shall also provide additional reactive compensation as per the quantum and time decided by reactive RPC in consultation with RLDC. So if you are any entity not provided adequate reactive power and there is a requirement due to the change in the system also, then certainly the RLDC and RPC can ask you that you need to provide additional reactive power support to these kind of places. So user and STU shall provide information to RPC RLD regarding the installation and healthiness of the reactive compensation equipment on regular basis. RPC shall regularly monitor and the status in this regard. Means all whatever reactive power compensation is planned, whether it has been installed or whether it is operating properly or not, its healthiness is ensured or not. So this is there. Okay. There is a plan. It is a old planning criteria. So let us avoid it. We will discuss the new one. These are the voltages I was telling you about. This is 5%, 5%, 10%. Okay. Nearly to 10%. Okay. So this is like this. So this is the operational limit, the higher voltage limit, lower voltage limit for the operation side. Then this is the temporary over voltage limits. Okay. So this is the temporary over voltage limits when there is sudden load rejection or kind of any issues are there in those cases. Then the how much imbalance that you can observe, that is also there. This is the voltage imbalance, 1.5% voltage imbalance at higher voltage level and lower voltage level 2% and further lower voltage 3% is allowed. This is as per the planning IGC as well as the CA grid standard. So we need to maintain this. Then each of the SLDCs, RLDC, NLDC, they have operating procedure for voltage control because it is very much required. So one thing is transformer tap change. So you can see that transformer is at HV side, HV, and this is LV side. So if both the voltages are HV and LV are on the higher side, okay, in this range, okay. So you need to plan reactor. You have to ask generator to maximize because there is no scope of tap change here. Tap change happen when there is a one side the voltage is high, another side the voltage is low. So like this situation or this situation, you can do change in the tap. While if you have both voltage on the higher side, plan reactors. If you have both voltages on the lower side, plan capacitor or remove reactors or switch off some of that. Take all the transmission line in service. Sorry, whatever, if any transmission line is out, you have to put those in service so that your voltage can further improve. Or in case here, remove the lightly loaded transmission line. So lot of things are there, means how the transformer tap changing is being done. Okay. Then HVDC, you do controlling of reactive power at HVDC terminal control. These are means being done very reactive power RPC controller is there at HVDC. So those HVDC RPC controller will do all this reactive power control. However, let us say if any HVDC is operating at zero reactive power, means zero active power, means it is not transferring any active power. Still there is a requirement of reactive power. Okay. So in those cases, how much reactive, how much means capacitor you have to put in service, because as soon as you have a capacitor put in service, AC filter basically, that is there at zero active power also, then it is causing the voltage to be higher side. But you at those kind of condition, you put only those filters which are very much required for the maintaining the HVDC at zero power flow, and so that you can immediately, if there is a requirement, you can immediately start increasing to the higher power flows, higher power orders. These are some of the drawings This is a schematic drawings where the operators gets high voltage can check high voltage, low voltage in the system. These are the voltages. Okay. This is, bus reactor, line reactor list through which they can check which reactor is on, which reactor is off, how much reactive power is available, or which reactive device is available for switching on and switching off. Then you have this megawatt as well as MVAR of the generators, how much with which generator is absorbing how much, whether there is a reactive power margin there, what is the power factor of that generator. If there is a margin available, I can ask those generator to absorb or inject reactive power. So this is the, means PQ diagram, basically the capability curve diagram it is. So based on analyzing this capability curve diagram, we can ask them that, okay, you are not following your capability curve. So you need to either follow the capability curve or we will issue a non-compliance messages to them. Then FSC, TCSC, transformer tap at what transformer tap is at what position, how much reactive power flow is being transferred. You can see that there is a very minimal reactive power flow flowing through this transformer. But some transformer, there is a good, very high reactive power flow that is going from this transformer. So you need to reduce this reactive power flows. Then monitoring of ICT taps, STATCOM, SVC devices, dynamic devices. You can see that this is the voltage and this is the reactive power. Okay. So then when there is a fault in the system, this voltage has immediately reduced. You can see there is a sudden, this reactive power from the STATCOM was 0. And as soon as there is a fault, immediately within millisecond, it went up to 225 MVAR. So this is why the STATCOM and SVCs are important, because they provide the dynamic reactive power support to the system. Okay. And during you can see that it is also having a deadband also. Means deadband, it doesn't provide any reactive power support. When deadband, when nominally the voltage is within the limit. Let us say the system condition is that it is within 1.01 to 1.03, not 1.1 to 1. Like 405 to 412. So it is not providing any support it is not trying to inject or absorb any reactive power. But as soon as the voltage are going beyond this limit, these STATCOM devices start injecting or absorbing reactive power into the system. So they act as dynamic devices as well as a static also. They are controlling both things. They have their dynamic part also and a static part also, which operates according to the system condition. If there is a fault, dynamic will come into the picture. If there is no fault and voltage is nominally increasing, then a static part, MSC, MSR will come into the picture. So this is how the STATCOM SVCs, we perform the cubic performance check. We do whether it is operating in the zone or not. And these are some of the operator action: high voltage, low voltage. So whatever you do in the high voltage, you just reverse the thing in the low voltage. Like first thing in the high voltage, switch on all the reactors, bus reactor. Switch on any line, switching in transmission line or tertiary reactor. So transmission line reactor or any reactor which is out of service. Generator near high voltage area to absorb more reactive power. SLDC should instruct to ensure all capacitor bank in high voltage to be made out of service. Optimize filter bank at HVDC terminal and possibility of routing of power on the AC line. If AC line is lightly loaded, reduce the HVDC power flow, increase the transmission power flow on the AC line so that it is loaded above SIL, so that the reactive power flow will reduce on this transmission line. Then transformer tap changing, then one by one. Last virtue is that if you don't have any option, then switch off the lightly loaded transmission line in the system. In case line which are made out, switchable line reactor is there, then you put the line reactor should be taken as a bus reactor. So this is the action you do in the high voltage scenario. Okay. Then in the low voltage, you do complete reverse. What have we done? We have taken this line out of service. So what we are doing? close the lines open to control high voltage, switch out the bus reactor, switching out the reactors. Then SLDC to ensure all capacitor bank in low voltage area in service, generator near low voltage area to inject more reactive power. Means you want low voltage means you need to have too much of reactive power injecting into the system, and high voltage you need to absorb that much of reactive power, or you move the whatever the reactive power which was causing the injection of reactive power, you remove them or you absorb the reactive power into from the system. So this is how this voltage control is being done. So this is the overall means what I wanted to convey for this. Just one thing that I wanted, this new transmission planning criteria has come already, has been from the March, and it will be applicable from the April. So if you go to, let me just provide you this. Normal and emergency limits, you can see that it is given. This is the normal limit and this is the emergency ratings already provided. These are the N-1 planning criteria. Different criteria are there for which on which our transmission system is planned. Coming back to the reactive power compensation. First, appropriate study has to be performed. Near to large RE complexes, synchronous condenser may be planned to provide dynamic support in addition to fax devices. If any fax devices is there, for further stability, you may need to plan synchronous condenser also. That has also been introduced. While planning bus capacitors, reactors, aspects such as voltage sensitivity due to the switching of these devices shall be considered. Means, let us say you are planning a reactor and you plan, let us say you are planning reactor of 120 MVAR and the fault level of that substation is very low. And if you switch on, switch off this 120 MVAR, this is going to result in very large reactive power change. Yeah, voltage drop. So certainly this sensitivity is not good because this will result in lot of issues to the operation guys, right? So you have to plan that switching should be such or the sizes should be such in place that you don't see a large particular node.
Sir,
Then a
what is
space
synchronous condenser?
provision, then
Sir, one question. So what is synchronous condenser we are planning for RA complex?
sir, it is just like means it is a generator, means basically you can see it as a generator, but it doesn't have any turbine side to it. Okay, means in the what you have in generator, that there is a turbine which is rotating the rotor, right? But here you are going to extract the energy from either some motor or something like that, so that you can rotate the rotor itself and you can able to absorb the reactive power from the system. So it is not going to generate any active power. It is only going to absorb or generate reactive power into the system. However, further you can put a flywheel to provide the inertial support. This is what we mean by synchronous condenser. So you have, okay, let me give a basic example. You have seen hydropower plant, right?
Yes, sir. Yes,
So
yes, yes, sir.
hydropower plant, what you have the generator is there, and then you can utilize the generation by providing through the nozzles or through the, means vein, through the pipe vein. You are
Fans.
providing the water through a very high, means altitude to low altitude and coming to the turbine and rotating the turbine, right? You decouple the turbine part. Okay, and then you rotate the generator using the electrical power. Turbine you decouple because turbine will require power from the means water source, right? Whatever the kinetic energy there. If you remove that, it will act as a basically as a motor, right?
Yeah, yeah.
So when it is acting as a motor, you go to the run it as a synchronous motor. Okay.
Yes.
And then you can control its excitation, right?
Okay.
By varying the reactive power to the controller, right? Reactive power, whatever the, sorry, the field current, you can increase the field current and decrease the field current. Na? You are that field current you are earlier where you were getting, that it is directly mounted on the rotor itself. Rotor was rotating from the kinetic energy. It was generator was generating, and that generator active power you are transmitting, or you are just converting into the DC power, and then it is feeding back directly to the motor itself, right? And that through that control you are changing the reactive power of generator by increasing or decreasing its field current, right? So here the field current input you will take it from the system itself. Means like let us say I am having a synchronous generator. I do not have any turbine input. Then what will happen to that generator if I want to rotate? If I am rotating the rotor, okay. If I'm rotating the rotor with the help of some motor, then what will happen? It will provide me inertial support because the rotor is rotating. And then what will happen is that it will provide changing the field current. I can absorb and inject reactive power into the system. So it's a device which will be injecting or absorbing the reactive power from the system by utilizing the active power from the system.
Okay, sir. Okay, sir.
So it's like that. Yeah. So you can search on the net. You will get a lot of things because this synchronous condenser provides you the inertia, dynamic voltage support, and it also helps us in improving the fault level at those RE point, RE complexes.
Okay, sir.
And this NGR is switching is there required basically single phase auto reclosure success. For that, you need to have a good NGR arrangement and you neutral grounding reactor. And for controlling the when you are trying to open this transmission line for voltage control, such lines, then you need to have a bypass arrangement so that you can utilize those switchable line reactor in those lines, long lines, as a bus reactor also. Okay. So that's why this NGR bypassing arrangement is required for the switchable line reactor, which you see that its loading will be varying depending upon the season to season. So you can either switch on the line or switch off the line. So when you switch off the line, utilize those line reactor as a bus reactor by bypassing the NGR arrangement. Then different reactive compensation shall be provided as far as possible in the low voltage system with a view to meet the reactive power requirement. Same cheese. It is the same, means whatever we have discussed, it is already the same philosophy that is required to be adopted. That you need to provide control reactive power at wherever the requirement is there. You don't put a reactive power. If you need to control voltage of 220 kV, then you don't need to put a reactor at 400 kV. Plan at 220 kV first. If that planning is not adequate, then you move to the 400 kV because the size of equipment at 400 kV can be on the higher side, right? Then the shunt reactor, you can see the sizes of shunt reactor at 765 kV. Either you can have 330 MVAR reactor or 240 MVAR reactor, 80 into 3 or 110 into 3. At 400 kV, you need to have a three-phase unit in generally 50, 60, 80, 125, 250. 125 into 2, if you place in parallel, it will be 250, right? Then you can have 220, 50, 25, 25 into 2, something like that. So these kind of reactor planning is there. Then shunt facts planning is required. It has to be done based on the sorry, stability criteria condition defined in the reliability criteria. And then this synchronous condenser, it is a synchronous machine operating without a prime mover. Okay. So there is no prime mover rotating the rotor. So reactive power input output regulation of synchronous condenser is performed by regulating the excitation current. You control the excitation current, and excitation current can be drawn from the system. The level of excitation current determines if the synchronous condenser generate or consume reactive power flow. And if you use that with a prime mover, then what you can do, you can utilize a flywheel kind of situation also, which will result in providing a active power support, the inertial support to the system also. Otherwise, it will be like non-moving device. So this is all on the part of how the reactive power planning is required to be done. All the planning will be done based on these limits itself, voltage limits. Already all these limits are prescribed and all the criteria are defined here. Okay.